The outer solar system contains thousands of objects whose motions are precisely tracked, and their orbits do not behave completely at random. This is a well-established observational fact. When consistent patterns appear in such data, astronomers treat them as meaningful signals rather than coincidences. For decades, textbooks have presented the solar system as a finished structure, with clearly defined planets and predictable dynamics. However, scientific understanding is not built on certainty, but on continuous testing of what we think we know. Recent research has introduced a new possibility, one that invites careful attention rather than immediate belief. Astronomers have identified subtle patterns in the motion of distant objects beyond Neptune. These objects, located in the outermost regions of the solar system, are not moving in entirely random ways. Instead, their orbits show slight but consistent deviations. Now here is the important teaching point. In astronomy, we often do not discover objects by seeing them first. We discover them by observing their effects. This method has historical precedent. The planet Neptune itself was identified through irregularities in Uranus's orbit before it was ever directly observed. In the present case, the proposed object has been informally named Planet Y. Unlike the widely discussed Planet 9, which is thought to be very distant and massive, Planet Y is expected to be smaller and significantly closer to the Sun. Its presence is not confirmed, but inferred through gravitational influence. To understand this, imagine placing a small weight on a stretched fabric. Even if you cannot see the weight directly, you can observe how the fabric bends around it. Similarly, astronomers study how gravity subtly shapes the paths of distant celestial bodies. When multiple objects show a shared pattern, it suggests a common cause. The key fact here is that these orbital patterns cannot be easily explained by the known planets alone. This does not immediately prove the existence of a new planet, but it does raise a precise and testable question. Are we still missing pieces of our own cosmic neighborhood? This question is not new. In fact, the search for unseen planets has appeared multiple times throughout the history of astronomy. Each time, it has forced scientists to refine their models and improve their methods. To understand why Planet Y is now being seriously considered, we must step back and examine how earlier generations of astronomers approached the same problem, often with far fewer tools, but equally sharp reasoning. That question has surfaced before, and each time it has reshaped our understanding of the solar system. The search for unseen planets is not a recent curiosity. It is a recurring pattern in the history of astronomy, driven not by imagination, but by precise inconsistencies in observed motion. When planetary paths do not align with prediction, scientists do not dismiss the anomaly. They investigate it. A clear example emerges from the early 20th century. In 1930, Pluto was discovered after astronomers noticed irregularities in the motion of Uranus and Neptune. At the time, Pluto was considered the missing piece, a gravitational source that could explain those deviations. Here is an important teaching insight. Discovery in astronomy often begins with a mismatch between calculation and observation. When equations fail to describe reality, it signals that something is incomplete in the model. However, as measurement techniques improved over the following decades, a problem became evident. Pluto's mass was far too small to produce the gravitational influence required to explain the earlier irregularities. What initially appeared to be a solution turned out to be insufficient. This created a deeper question. If Pluto was not responsible, then what had caused those observed deviations in the first place? In some cases, improved data resolved earlier measurement errors, but in other cases, uncertainty remained. To understand this logically, consider a simple system. If multiple objects are moving under known forces, their paths can be predicted with high accuracy. If those predictions fail, there are only two possibilities. Either the measurements are incorrect, or there exists an additional influence that has not yet been accounted for. Astronomy progresses by carefully distinguishing between these two possibilities. In recent years, the quality and quantity of observational data have increased significantly. Advanced telescopes and long-term surveys now track distant objects with far greater precision than was possible even a few decades ago. This has allowed scientists to revisit earlier questions with new tools and stricter analysis. As a result, the idea of unseen planetary bodies has not disappeared. Instead, it has been refined. The question is no longer based on isolated anomalies, but on patterns emerging from large datasets. This shift from individual observation to statistical analysis marks a critical transition in modern astronomy. To move forward, researchers began examining not just single objects, but entire populations of distant bodies, searching for consistent structures within their motion. It is within this broader and more rigorous framework that the current hypothesis begins to take shape. Building on this shift toward large-scale data analysis, the investigation reached a more rigorous stage in August 2025. At this point, the question was no longer whether patterns might exist, but whether those patterns could withstand systematic examination. A team of astrophysicists from Princeton University approached this problem with a clear objective. Instead of focusing on isolated anomalies, they analyzed a large population of distant objects located beyond Neptune, commonly known as Kuiper Belt objects. Their dataset included more than 150 such bodies, each with carefully measured orbital parameters. Now, here is an important teaching point. When dealing with complex systems, individual cases can often be misleading. Patterns that appear significant in a small sample may disappear when viewed in a broader context. This is why modern astronomy increasingly relies on statistical consistency rather than isolated observation. The researchers Amir Siraj, Christopher Chiba, and Scott Tremaine applied this principle directly. Their goal was not to explain one unusual orbit, but to determine whether a consistent structure existed across the entire dataset. To understand their method, consider a simple analogy. If you observe a single leaf moving in the wind, its motion may seem random, but if hundreds of leaves begin to move in a coordinated direction, you immediately infer the presence of a common force. The same logic applies here. Each object's orbit may appear complex on its own, but collectively they can reveal underlying patterns. What makes this study significant is not just the size of the dataset, but the precision of the measurements. Advances in telescope technology and long-term observational programs have made it possible to track these distant objects with increasing accuracy. This reduces uncertainty and allows subtle trends to become visible. The team carefully examined orbital orientations, inclinations, and spatial distributions. Rather than asking whether any single orbit was unusual, they asked whether the overall configuration deviated from what would be expected under known gravitational influences alone. The result was not immediately obvious, but it was consistent enough to demand attention. A pattern began to emerge, one that could not be easily dismissed as random variation or measurement error. This is where the investigation takes a decisive turn. When a statistically significant structure appears across a large dataset, it shifts the discussion from possibility to hypothesis. The next step, therefore, was to identify the nature of this emerging pattern and determine what kind of physical mechanism could produce it. That emerging pattern, once isolated, required careful interpretation rather than immediate conclusion. The researchers began by removing the most obvious source of gravitational influence in that region, Neptune. This step is essential in scientific analysis. Before proposing a new cause, all known causes must be accounted for and mathematically removed from the system. After this correction, a subtle but consistent structure remained. The orbital planes of objects located between approximately 80 and 200 astronomical units from the Sun were not randomly distributed. Instead, they exhibited a slight tilt, a uniform deviation from what would be expected if only known gravitational forces were acting. Now, it is important to understand the scale involved. 1 astronomical unit is the distance between the Earth and the Sun. At distances beyond 80 astronomical units, these objects are operating in a region where gravitational influences are weak and dispersed. In such an environment, randomness is typically the dominant expectation. Here is the key teaching insight. When randomness is expected, but order is observed, it indicates the presence of an underlying constraint. In physics, such constraints are almost always linked to forces. The observed tilt was small, but statistically significant. This distinction is critical. A small effect can still carry strong meaning if it appears consistently across many independent observations. In this case, the alignment was not based on a few objects, but on a broader population, which reduces the likelihood of coincidence. To visualize this, imagine a large number of spinning disks scattered in space. If each disk tilts in a slightly different direction, the system appears random. But if many of them lean in the same direction, even by a small angle, it suggests that something is influencing all of them in a similar way. The same logic applies here. The Kuiper belt objects in this range are not behaving as independent systems. Their shared tilt implies a common external influence acting over vast distances. Importantly, this alignment cannot be easily explained by known planetary forces alone. Neptune's influence, once removed, does not reproduce the observed structure. This eliminates the most immediate explanation and strengthens the need for an alternative. At this stage, the discussion shifts from observation to interpretation. The question is no longer whether a pattern exists, but what physical mechanism can produce it. One possible explanation is the gravitational pull of an unseen massive body, orbiting the Sun at a distance where it can subtly influence these objects without being easily detected. However, before accepting this explanation, scientists must test it against all other plausible scenarios. Only through comparison can a hypothesis gain credibility. This leads directly to the next phase of the investigation, where competing explanations are systematically evaluated. At this stage, proposing a new planet is not the first step. It is the last step, taken only after all other explanations have been carefully examined and tested. The researchers approach this phase with a clear methodological principle. Any observed pattern must be explained using known physics before introducing a new object. This is a fundamental rule in scientific reasoning, often summarized as choosing the simplest explanation that fully accounts for the data. They began by evaluating interactions within the Kuiper belt itself. Since this region contains numerous small bodies, it is reasonable to ask whether their mutual gravitational influences could collectively produce the observed orbital alignment. However, detailed simulations showed that these interactions are too weak and too chaotic to create a consistent, large-scale tilt across many objects. Next, they considered the gravitational effect of the Milky Way galaxy. At very large distances, galactic tides can influence the motion of objects in a solar system. This effect is well documented in the study of long-period comets. However, in this specific range of 80 to 200 astronomical units, the galactic influence is present, but not strong enough to produce the precise pattern observed in the data. Another possibility involved past stellar encounters. Over billions of years, nearby stars can pass close enough to disturb the outer regions of a planetary system. Such events can leave lasting imprints on orbital structures, yet, when modelled, these encounters tend to produce irregular and scattered effects, not the kind of uniform alignment identified in the dataset. Here is an important teaching insight. A strong scientific explanation must not only be possible, it must be predictive. It should reproduce the observed pattern consistently, not just occasionally or approximately. When each of these alternative scenarios was tested, they failed to match the data with sufficient accuracy. Either the effect was too weak, too inconsistent, or required additional assumptions that reduced explanatory clarity. In contrast, a single additional planet, placed within a specific range of mass and orbit, was able to reproduce the observed alignment with far greater precision. This does not confirm its existence, but it demonstrates that such a model is both simple and predictive. This distinction is crucial. Science does not accept an idea because it is interesting. It accepts it because it explains observations more effectively than competing models. At this point, the hypothesis of a previously undetected planet emerges not as speculation, but as the most consistent explanation available within the current framework of data and physics. The next logical step, therefore, is to define the properties of this proposed object. If it exists, what would its size, orbit, and mass need to be in order to produce the observed effects? With competing explanations systematically tested and found insufficient, the investigation moves into a constructive phase. The question now is not whether an unseen influence exists, but what form it must take to produce the observed effects. To answer this, researchers turn to simulation. By introducing a hypothetical planet into their models and adjusting its properties, they examined which configurations could reproduce the orbital alignment seen in the data. Here, it is important to understand the role of simulation in modern astronomy. We cannot manipulate planets directly, but we can recreate physical conditions using well-established laws of motion and gravity. If a model consistently reproduces real observations, it becomes a strong candidate for explaining reality. The results provided a constrained range rather than a single value. Planet Y is estimated to have a mass between 25 and 450 times that of Pluto. This range may appear broad, but it reflects the limits of current data and the sensitivity of orbital dynamics to mass variations. To place this in perspective, Pluto is relatively small compared to the major planets. Even at the lower end of this estimate, Planet Y would be significantly more massive than Pluto, while still remaining far smaller than Earth. At higher estimates, it approaches the scale of the inner rocky planets. Its orbital distance is equally important. The simulations suggest a position between 100 and 200 astronomical units from the Sun. This places it well beyond Neptune, yet not as distant as the previously hypothesized Planet 9. In practical terms, this means it occupies a region that is both difficult to observe and dynamically influential. Another defining feature is its orbital inclination. Planet Y is predicted to orbit at an angle of approximately 10 to 15 degrees relative to the primary plane of the solar system. This tilt is not arbitrary. It aligns closely with the deviation observed in the Kuiper belt objects, reinforcing the internal consistency of the model. Here is a useful teaching insight. In physics, a good model does not just explain one feature. It explains multiple independent observations using the same set of parameters. In this case, mass, distance, and inclination together produce a coherent explanation. Despite this clarity, one crucial point remains. These characteristics are inferred, not observed. Planet Y has not yet been directly detected by any telescope. This distinction defines the current stage of the investigation. The hypothesis is now precise and testable, but it remains provisional. The next logical question, therefore, is not about its properties, but its origin. If such a planet exists in this region, how did it come to be there in the first place? Once the properties of this proposed planet are constrained, the next question becomes unavoidable. If such an object exists at this distance, how did it arrive there? This is not a trivial question. The outer solar system is not a region where planets are typically expected to form in isolation. The distribution of material, temperature, and gravitational interactions during the early stages of planetary formation makes such an outcome unlikely without a specific mechanism. Scientists have proposed three primary scenarios, each grounded in known physical processes. The first possibility is that Planet Y formed within the solar system itself, closer to the region of the giant planets. During the early stages of planetary formation, gravitational interactions were far more dynamic than they are today. Large bodies could be scattered outward through repeated encounters with Jupiter or Saturn. In this scenario, Planet Y would be a native object, displaced from its original position and stabilized in a distant orbit. Here is a useful teaching insight. Planetary systems are not static during their formation. They undergo periods of instability where objects can migrate significant distances. This process is well supported by models of early solar system evolution. The second possibility is capture. In this case, Planet Y would not have formed around our Sun at all. Instead, it could have originated in another stellar system and later been captured by the Sun's gravitational field. While this may seem unlikely, it becomes more plausible when we consider that stars often form in clusters. During these early phases, close encounters between young systems can allow objects to be exchanged. A simple way to understand this is to imagine two nearby systems interacting briefly. Under the right conditions, a smaller body can lose enough energy to become bound to a new star. The third scenario involves a more complex interaction with other proposed objects, such as Planet 9. In this model, multiple distant bodies could exist simultaneously, influencing each other's orbits over long timescales. Together, they could shape the structure of the Kuiper belt in ways that a single object might not fully explain. Each of these scenarios carries different implications. A scattered native planet supports models of early dynamical instability. A captured object suggests interactions between stellar systems. A multi-planet configuration points toward a more complex outer solar system than currently understood. At this stage, no single explanation can be confirmed. However, defining these possibilities allows scientists to frame the problem more precisely. The next step is to consider how such an object would be classified if it were observed. Its origin is one question, its status within the solar system is another. With possible origins established, the discussion now shifts from formation to definition. Even if such an object exists, an important question remains: how would it be classified within our current understanding of the solar system? Astronomy does not rely on informal labels. It uses precise criteria to define what qualifies as a planet. These criteria were formalized in 2006 by the International Astronomical Union, following extensive debate within the scientific community. According to this definition, a planet must satisfy three conditions. It must orbit the Sun, it must have sufficient mass for its gravity to shape it into a nearly spherical form, and it must have cleared its orbital region of other debris. The third condition is particularly significant. It distinguishes planets from smaller bodies such as dwarf planets, which share their orbital space with many other objects. This distinction became widely known during the reclassification of Pluto. Now, applying these criteria to planet Y requires careful reasoning. Based on the estimated mass range derived from simulations, this object would be substantially more massive than Pluto. At approximately 50 times Pluto's mass, it would exert a much stronger gravitational influence within its orbital region. Here is a useful teaching insight. The ability to clear an orbit does not mean removing every object. It means becoming the dominant gravitational presence in that region, such that other objects are either absorbed, ejected, or forced into stable, subordinate paths. At distances between 100 and 200 astronomical units, the density of surrounding material is relatively low. This makes it easier for a sufficiently massive body to dominate its orbital zone. Even a planet smaller than Earth could achieve this under the right conditions. This leads to a logical conclusion. If planet Y exists within the predicted mass and orbital range, it would likely meet all three criteria defined by the International Astronomical Union. In that case, it would not be classified as a dwarf planet, but as a true planet. This possibility carries broader implications. The addition of a new planet would not only expand the solar system's inventory, but also reopen discussions about how planetary classification is applied, especially in distant and less densely populated regions. However, classification depends on confirmation. Without direct observation, these conclusions remain conditional. At this stage, the hypothesis is well defined, but not universally accepted. Some scientists remain cautious, proposing alternative interpretations of the same data. To evaluate the strength of this idea, it is necessary to examine these competing viewpoints and understand the basis of scientific skepticism. At this point, the hypothesis appears internally consistent, but scientific acceptance does not depend on consistency alone. It depends on scrutiny. In any rigorous field of research, a strong idea must withstand critical evaluation from multiple perspectives. This is not opposition for its own sake, but a necessary process to ensure that conclusions are not drawn prematurely. Several astronomers have raised important objections to the Planet Y hypothesis. Their concerns focus not on dismissing the observed pattern, but on interpreting its origin differently. One alternative explanation suggests that the orbital alignment could result from the combined gravitational influence of many smaller objects in the outer solar system. While each individual object exerts only a weak force, their collective effect over long timescales might produce a measurable structure. Here is a useful teaching insight. In complex systems, large-scale behavior can sometimes emerge from the interaction of many small components. This is a principle seen in fields ranging from physics to biology. However, this explanation faces a challenge. When modeled in detail, such distributed interactions tend to produce diffuse and irregular patterns, rather than the relatively coherent alignment observed in the data. Another concern involves observational bias. The detection of distant objects is not uniform across the sky. Certain regions are observed more frequently or with greater sensitivity. This can create the appearance of patterns that are, in reality, artifacts of how the data was collected. To understand this, consider a simple example. If you only observe a system from one direction, you may miss variations that would be visible from another angle. As a result, the data may appear more structured than it truly is. Researchers working on the Planet Y model have attempted to account for these biases, but the possibility cannot be completely eliminated. This is why independent observations and expanded datasets are essential. Despite these criticisms, the proposed model retains an important advantage. It explains the observed alignment using fewer assumptions and produces results that closely match the data. This does not make it correct, but it makes it competitive. At this stage, the discussion reaches a defining boundary. Theoretical models, no matter how refined, cannot replace direct evidence. The only definitive test is observation. Either the object will be detected, or alternative explanations will prove more accurate as new data becomes available. This shifts the focus from analysis to discovery. The question is no longer whether the hypothesis is plausible, but whether it can be verified. To answer this, astronomy now turns to a new generation of observational tools capable of exploring the outermost regions of the solar system with unprecedented detail. With the focus now shifted from theory to observation, the search enters its most decisive phase. The question is no longer how Planet Y might exist, but whether it can be detected. Modern astronomy relies on systematic sky surveys rather than isolated observations. Among the most significant of these efforts is the Vera Rubin Observatory in Chile. Its primary mission is not to look at a single object, but to repeatedly scan large regions of the sky over extended periods. This approach introduces an important methodological advantage. Instead of capturing a static image, astronomers observe motion over time. Even extremely faint objects can be identified if their position changes consistently against the background of distant stars. The observatory's legacy survey of space and time is designed precisely for this purpose. It will collect vast amounts of data, allowing researchers to track slow-moving objects located at the far edges of the solar system. At distances between 100 and 200 astronomical units, detection becomes inherently difficult. Objects at this range receive very little sunlight, making them extremely dim. In addition, their orbital motion is slow, requiring observations over months or even years to establish a clear trajectory. Here is a useful teaching insight. In observational astronomy, difficulty is not defined only by distance but by contrast and motion. A nearby object can remain undetected if it is too faint or moves too slowly relative to background noise. Despite these challenges, the methodology is robust. By comparing repeated images of the same region, astronomers can isolate objects that exhibit consistent displacement. Over time, these small shifts accumulate into measurable orbital paths. If Planet Y exists within the predicted range, this approach should eventually reveal either its direct image or its gravitational influence on nearby objects. Both forms of evidence are valid, but direct detection would provide definitive confirmation. If such a discovery occurs, it would mark the first addition to the solar system's planetary inventory in nearly 2 centuries. More importantly, it would validate the use of large-scale statistical analysis in uncovering unseen structures. However, an equally important outcome must be considered. If no such object is found, the data will still refine existing models. It may reveal new complexities in the Kuiper belt or expose limitations in current assumptions about orbital dynamics. This reflects a central principle of science. Progress is not dependent on a specific outcome, but on the improvement of understanding. The search for Planet Y, therefore, is not simply about finding a new planet. It is about testing the limits of our models, our tools, and our assumptions. And in that process, regardless of the result, our view of the solar system becomes more precise. The investigation continues,